Today, Milad Mozayyani, Patel, Brian Dunn, and Doug Belgorod will be presenting a brief overview on our FARMS drone idea. FARMS stands for Farming Aerial Reconnaissance, Monitoring, and Spraying.
Our target stakeholders are primarily farmers, venture capitalists, forest services, government entities such as national parks agencies or the EPA, and ourselves, the startup employees. We are presenting this idea today as a method by which we can increase the cost efficiency of crop spraying and the ease by which crop health can be monitored. Traditional methods of crop spraying often involve hiring third-party laborers to perform high-altitude aerial applications of fertilizers, which results in uneven spraying and wasted product. Collecting data on crop health takes valuable time from a farmer's day as they have to trek out into the fields and collect samples by hand. The goal of this project is to improve the efficiency and quality of data collection for farmers while reducing the cost to do so. The objectives are to build a versatile autonomous system capable of replacing the need to hire services and travel around a farm to collect data, as well as to collect new data that has been previously underutilized.
Our concept of operations provides a brief visual overview of the various missions our drone system will be able to perform. The drone is designed to be modular and tailored to each of the three mission types, keeping weight low and ultimately operation costs as well. The drone is easy to configure and should take anywhere from 5 minutes to 15 at maximum to set up. Preliminary estimates show that we will be able to spray crops at a rate of 44 acres per hour, collect 10 points of soil samples per hour, and scan 130 acres per hour, all utilizing pre-programmed flight paths. At the end of each mission, the drone will return home on its own, where it will be able to fully charge in around half an hour. The top-level requirements developed to meet our goals include multi-mission type functionality, such as the ability to collect crop health data, crop spraying functionality, and the collection of soil samples. Our aircraft shall be capable of flying each mission autonomously after being programmed by the user, while following all FAA regulations on autonomous vehicles. In the end, we shall have a system capable of utilizing multiple drones operated by just one user.
The project lifecycle totals up to 13.5 weeks. To start the progress, we'll meet with farmers to establish requirements and desires for the drone. Then we'll create preliminary designs and choose one to continue improving over time. Once all parts and software are finalized, orders and contracts will be sent out. Then the test aircraft will be constructed 9 months since starting and tested for 4 months before being released for purchase. After that, we will continue taking feedback on the product to increase quality.
Here, the system architecture displays the overall structure of the system as well as the relationships between the two main subsystems, the drone and ground control. By highlighting the different options the drone has once it begins a mission, the architecture reflects the most attractive feature of the system, its ability to seamlessly accomplish multiple agricultural functions. As a conceptual overview of the structure of the system, this architecture illustrates the requirements of the different subsystems, such as the ground control needing to provide a flight plan for the drone. While the farmer is not explicitly shown, his responsibilities in the operation are clear through the interaction of the drone and ground control. The project breakdown structure is a way of breaking down every element of our system into a hierarchical framework that shows how each component is related to one another. We start up top with a brief reiteration of the FARMS drone mission statement. From there, we break up into the two main facets of our system, the drone and ground control. Under the drone subsystem are the best attributes of the system, including the detachable wing assembly and the multi-purpose sensor system. The process of separating these components further and showing their relationships to each other makes it easier to understand the functions of each component and its contribution to the system's mission of effectively monitoring and spraying crops. Also, this depiction of the system intuitively describes the requirements of components at each level and their relation to one another. As the work breakdown structure is derived from the project breakdown structure, it includes the drone and ground control as subsystems, but also designates the work and services required to complete this project. In tandem with the project lifecycle, this diagram demonstrates the work that is crucial for the duration of the project, from the early stages of research and development to any post-sale maintenance of the system. Since this project cannot be done by our team alone, it is important that the work breakdown structure contains the other entities responsible for services, in our case, potential consumers and software developers. The diagram is organized to chronologically reflect the different stages of development, which for this project is the most intuitive way to view the work. Similarly to how the project breakdown structure reflects the requirements of the system, this work breakdown structure exhibits the requirements of the people involved as well.
The digger's function is to fly to points predetermined by the user and collect soil samples. The craft starts by computing the flight path to the nearest point and the points following. The aircraft will reach each point, dig a sample, and organize the sample based on the point it was collected at. Then, at the end of the mission, the aircraft will return to the user-designated landing location to dispense the samples. For the scanning function, the user will designate a flight path for the drone to follow. The drone will follow the path and scan the field with its onboard IR camera and will simultaneously construct an IR map of the field that will then be formatted for export once the drone reaches its designated landing location. The map can be collected by a USB on the drone itself by simply plugging in a USB drive and pressing the export button on the drone. The spraying function requires the drone to be in fixed wing mode. The user will designate the flight path and the drone will vertically take off and then switch to forward propulsion located on the wing. The drone will follow the path and spray the field with any fluid that is stored in the wings, and at the end of the mission, will return to the designated landing location.
This slide shows the mission timeline for the digger-equipped drone. It will take about 10 minutes to configure the drone by setting up the appropriate attachments to the main body. The flight path will then be initialized for another 10 minutes. The quadcopter will power up and launch in about 5 minutes. It will take about 60 minutes for the digger to collect samples from 10 points in 50 acres. After all the samples are collected, it will take about 10 minutes to fly back, then about 5 minutes to land, power down, and offload the samples. The process is pretty similar for the scanner and sprayer. The scanner will take about 5 minutes for setup and it will analyze 130 acres in an hour. The sprayer will take 15 minutes to set up and spray 44 acres in an hour.
The following are the requirements for the drone subsystem. Max takeoff weight shall not exceed the FAA mandated 55 pounds, and the aircraft shall operate at an altitude of anywhere between 12 to 36 feet. Furthermore, the drone shall fly as both fixed wing and quadcopter, and will follow a pre-programmed flight path during its mission. The drone will support modifiable sensor and tool attachments depending on the mission, and shall maintain steady flight in winds on a Beaufort scale of 6, approximately 25 knots. Also, the drone shall export data from the onboard computer to the user. The following are the requirements for the ground control subsystem. Ground control shall provide backup controls for the operator in case of any emergency. Ground control shall also charge the drone in 30 minutes from zero battery and shall track the position of the drone during the entire mission. Most importantly, ground control shall receive flight path inputs from the user and subsequently provide a mission-specific flight plan for the drone.
Here we observe the change in margin percentages for one technical performance parameter, the weight of the drone. Due to FAA restrictions, the maximum value rests at 55 pounds, and the margins decrease as the project nears completion. Also included on the graph is our best estimate at each step in the project, exhibiting a linear trend toward the maximum possible value. Throughout the project, these estimates will change, and depending on their value, the team will have to make decisions on whether to act or trust the trend. More technical performance parameters were observed in a similar fashion, such as battery time, spray speed, and map definition.
At the end of our project, we have planned to implement a methodology to verify that all of our goals and requirements are met. This will include beta testing with select farmers to ensure our mission times, charging times, and automation abilities all meet or exceed our stated estimates. Once the technology proves successful, we will monitor the crop yields and profit margins of volunteer farms using the drone system over a 5-year period. Barring any natural disasters, we will then be able to use this data to accurately assess the profitability and efficiency of our system.